Cindy made it. Will you let her know I said yay? When you get a chance, I'm sorry. How's it going, Tanner?
Hello.
Just waiting for everybody to come in. It's only 3 minutes for class. I'm surprised there's not more people in here already, but it is what it is, I reckon. You have any questions before we get started?
No, I think I'm all right for right now, but thank you.
No problem. I'm loading up the e-text now. Let another person in. Hey, Drew, feel free to ask me any questions. We only got a couple minutes before class starts, and there's only you and Tanner in here so far.
Sorry, I didn't have audio yet. What'd you say?
Oh, no problem. I said, hey, Drew, glad you came. And if you have any questions, you can go ahead and ask them. We only have a couple minutes before class starts, but there's only you and Tanner in here so far.
Okay. Was the chapter 21 and 22 practice test due last night, right?
I don't recall setting up anything to be due last night for testing or anything like that, but I was planning on opening a new test or two new tests this week and probably tonight. So I'll have to double check to make sure, but I don't think I had any such plans.
Because in Canvas it says the 21 and 22 was locked at the 9th.
Gotcha. 21,
And
22. Let
the
me
practice
double check.
test, yeah.
Gotcha. I'm gonna go back to my modules and see what's going on there. Okay. Yeah, it was July 9th, practice test 3, but I don't think I ever did make test 3. Yeah, don't worry about it. You didn't miss anything. That's the test that I'm going to open back up in a few, probably tonight, in fact. And we're going to have that one, and we're going to have a test. I guess technically that one will be made test 4, and then we'll have a test 5 that covers 23 and 24 that I'll make open probably today as well. But you'll have at least until probably Wednesday or Thursday of next week to get that one done. But the one on 21 and 22, you'll have till Sunday to get done.
All right, sounds good. Thank you.
No problem. All right, we got some more people in here. Hey, Gabrielle.
Hey, Professor.
Have any questions for us? It's only you and two other people so far. But if you
I
have any
do have a
questions,
scheduling question.
okay.
Do you know what we would be doing on July 24th? That's a Monday in 2
July
weeks.
24th. My suspicion is that we should be roughly on chapter 29, somewhere around there.
I just wanted to make sure we didn't have like a test that day
I don't
because
recall having one scheduled on that day. If you did, if you let me know in advance, it's okay. We can, work it out. And like I said, I have the ability to do the online test where you're actually proctored. So even if you have to miss the actual day, you can still do it maybe later that night or something.
Okay, thank you.
No problem. But yeah, let me know when you get closer to it. Stolen just came in and it looks like it's basically time to start. So I should probably go ahead and get cracking just because time is of the essence and we're already behind because we missed a day to storm. We missed a couple days due to just vacations and letting people out early and all sorts of stuff like that. Although the online classes were not supposed to, I'd still feel kind of bad for if I, hold classes on those days and someone has to miss. So anyways, we're going into chapter. There I go with the yawns again. We're going into chapter 24, and this is where I can introduce you to this new paradigm, is what I'm calling it, where basically there's a series of 3 major steps that you have to take to actually calculate the capacitance of a geometric configuration of plus and minus charges. So the typical capacitor is just a parallel plate capacitor, has a surface area A, has a separation distance D, and usually can be separated by some kind of insulator, which we're going to use the fancy word, not insulator, but the fancy word dielectric for that. And that's supposed to just, one, structurally give it the ability to stay separated, 2 conductors loaded up with positive charge on one side and negative charge on the other side. Obviously, they're attracted to each other because they're opposite charges, and they're wanting to touch. And not only that, electricity is wanting to fly across there. So when you have air in it, we know that when the electric field between those plates becomes on the order of 3,000 volts per, or excuse me, 3 million volts per meter, then it will actually become a conductor. So the air actually turns into a conductor at that point. So if you put a dielectric in there, 1, you get the structural stability of keeping the thing separated, and 2, you can often get a larger breakdown voltage for the dielectric than you have for air. And then there's a third effect that if you look at the last sections of this chapter, you'll find that basically when you put a dielectric between the plates, it creates an electric field or the equivalent of electric field pointing in the opposite way. So it actually weakens the electric field between the plates. And that could also, of course, make it less likely to break down. So we're going to try to do 3 particular examples today regarding that new quote unquote paradigm. And the 3 steps, y'all can check this again on the video later, or you can write it down now in real time. The first step is we're going to use Gauss's law, or in principle, you could use Coulomb's law to, yes, Drew, we had covered chapter 23. That was what I finished, not Wednesday because we didn't meet, but I'd finished it basically on Monday. When I finished the law, surface integrals, and then I did those special shapes. The videos are uploaded from, I think it was what's the day, the 10th, so it'd be 7/3 was the video for that one. So the first step, like I said, is since the Coulomb's law, at least the integral version of Coulomb's law, can in principle be used to figure out the electric field for any configuration, as long as you have access to like a computer and can write code and stuff regarding turning that integral into code, then you can do anything with it. But generally the paradigm exists for us using Gauss's law to create or find an electric field as a result of a positive charged plate or something and a negatively charged, equally charged plate of something. So for instance, it could be 2 parallel plates like I just discussed. It could be a inner wire through the middle with a coaxial cylindrical shell on the outside. The inner wire would have a charge, say plus Q, and the outer wire would have a charge of minus Q on the inside surface of that cylindrical shell. Or you could have a spherical conductor on the inside, and on the inside surface of a spherical shell concentric with that sphere, you could have a negative charge, say. Those are 3, and the 3 symmetries that you could use Gauss's law to actually compute capacitance with. So that's what I'm saying. The first law, the first step of this paradigm is using Gauss's law, probably, but possibly Coulomb's law. The second step is using the change in voltage is equal to the negative integral of E dot dl to find the voltage difference between the two plates. So you've got to, of course, have the electric field between one plate and the other, and then you got to integrate. Ideally, you want to integrate from the low voltage side, which would be the negative plate side, to the high voltage side, which would be the positive plate side. And when you integrate in that direction, the negative integral of E dot dl, you should get a positive voltage. Now, finally, you can take the third step, which is the definition of capacitance, which is the charge held per unit voltage. So you take the charge that is contained by that geometrical capacitance and divide it by the voltage across that geometrical capacitance. And that gives you the actual capacitance of the capacitor. And of course, when you're finished with that, there should be no remnants left. That's why I keep using the word geometrical. There should be no remnants left suggesting charge density, linear charge density that we called lambda, sigma, the charge density that we call that was charge per unit area, r rho, the charge per unit volume, rq, or anything like that. So your capacitance should be a purely geometric formula. And that's the big paradigm. One of the big paradigms for this course is using that three-step process to compute Gauss's law, or excuse me, capacitance using Gauss's law and the integral. When we get to magnetism, we're going to have a similar paradigm, but in that case, we're going to use Ampere's law or the law of Biot-Savart, and that'll allow us to calculate a magnetic field. Then once we have the magnetic field, we'll use the definition of magnetic flux, which is the integral of B dot dA. We'll use that to calculate a flux. And then we'll use the definition of self-inductance to calculate the inductance of a structure, some kind of electronic instrument or device, if you will, that you use in a circuit. In this case, it's an inductor. One of the examples of an inductor, for instance, is a solenoid. So if you take, wire and you wrap it preferably very smoothly, that makes an intense magnetic field, and it acts as a solenoid, which is an inductance. Also, if you took that inductor and you bent it around to the shape of a donut, then it'd be called a toroid. You can also fill that space inside of the solenoid, the wrapped wire. You can fill that, for instance, with iron to have certain properties that'll help. And you can do the same thing with the toroid as well. So we're going to have another paradigm that you got to do, and you can see them on my YouTube channel, but also I've given you links to them within your Canvas pages. So anybody have any other questions before we get cracking on this chapter 24 stuff? Boy, chapter 3, that's a long time ago. No? Okay. All right. Well, we don't have very many people tonight. We only got 7. So let's just go on and make sure you ask me questions as you have them. So first off, I want to share my screen, but rather than share my screen with my iPad, I'm going to start off with sharing the screen of the book. And I just wanted to show you that this is what capacitors look like. That actually is a capacitor, that little red chiclet looking thing, that little bluish colored, I wouldn't say a Tic Tac, but Tylenol pill looking thing, that's a capacitor as well. These cylindrical shapes, they're capacitors. That one right there is probably a diode, maybe a Zener diode or something like that. But you can see sometimes these capacitors will have like a blue or a black cover, and they might have a silver top or a different color top, and on that top might be a little Mercedes symbol. That's a good indicator for you, because it pops open when the actual capacitance has burst or basically failed. That'll just pop open, and you can look in and you see a capacitor, and you see this, what used to be a Mercedes symbol, except the 3 tabs of the aluminum that it's made of have popped loose. And this has saved me a good deal of money personally. So I'll just tell you, one, never work on electronics equipment until you unplug it, and two, unplugging it is not a guarantee that you will not be killed by it. Okay. And these capacitors are part of the problem with that, because you can unplug a electrical circuit, for instance, a TV, as I did, for instance, and you can unplug it, and still there will be capacitors in the circuit that are still charged. And if you inadvertently cross between a high voltage and a low voltage situation, our positions in the circuit, you could actually get electrocuted. And I'm saying that with a giggle in my voice because I almost did. Okay. So just be careful if you try this stuff. Really what you have to do to make sure, or to try to make sure that you're not going to hurt yourself, is once you unplug it, then you sort of need to go around with a ground wire and make sure you touch all the terminals of all the capacitors and stuff like that. Just to make sure everything's grounded. If that's the case, then you'll be pretty safe. Okay. Not only that, every time you go to work on a particular wire or a particular device within an electronic circuit, you want to check the voltage on each side relative to ground, as well as on each side relative to itself, just to make sure that there's no real voltage there. If that's the case, then you have a modicum of safety worries removed, so you can mostly work on it. So the reason why I'm telling you this is when I was working before 9/11, I had a really cool job I loved. I had not that I don't love teaching, but this one was like really high paying, and I loved because the work was awesome. I worked with really smart people. We had they had a basketball court for us. They had ping pong courts or ping pong tables for us, and all sorts of cool stuff. Free medical, dental, or I say free, but our benefits included all paid medical, dental, and vision insurance for me and all my dependents, and it was a appreciable salary. And of course, I went out after feeling pretty comfortable in the job and knowing I love it. I went out and bought me a decent vehicle. It was the first time I had a new vehicle. And then I bought me a TV and a living room suite because I just bought a house as well. And I bought a TV. It was an HD TV. And this is like just when they were coming out. And it had like 980 pixels or some god awful, quote unquote big number. But they were so new at the time. I think I ended up paying like $5,800, $5,500, something like that for this TV that was a 43-inch, and it had a huge box on it and this sort of stuff. But it was a nice TV, and it had way better picture than any other ones I saw in the store. So I went ahead and bought it, and I loved it, and it worked for years. After 9/11, I got paid off. I got laid off basically, and lost my job. But luckily, I had stock options too, so I was able to cash them in, and that let me live for another half a year until I could find another job. I was working at Home Depot, and I was painting cars and doing drywall work and all sorts of good stuff. But anyways, the key to the story is about 12 years down the road, we still have said TV, and now I'm a teacher, so I'm not making any money. And I go to turn TV on, or my daughter goes to turn TV on one morning, and it just goes like shuts down. I'm like, crap. So I call a TV repairman, and they're talking like $175 just to show up, and then it's going to be like $75 an hour plus parts and all that stuff, and they're going to charge me for travel. I'm like, God, man, this is brutal. I can't afford all that. So on a whim, I just opened up the back of the TV, and I looked, and there's a capacitor. It looks just like that dark blue with the light blue stripe. It looks just like that, only bigger. It's a much bigger size. And I looked, and that little Mercedes symbol had popped right up. I have a kit, electronics kit, where I taught basically a honors physics, calculus-based physics class, and it had a lot of various items that you'd use in electric circuits. It had certain gauges of wire. It had resistors, thermistors, capacitors, diodes, and all sorts of good stuff, transistors. And I looked, and I just happened to not only have the exact right 1000 microfarad capacitor, I also had the 1000 microfarad capacitor that went up to the temperature range that this one went up to. So I knew I was in a good place. So of course the thing's been unplugged. I thought I had thoroughly done everything as far as grounding everything, but I did find that capacitor was bad, and I went ahead and cut it out. And in the process, I don't know what happened. All I know is all of a sudden I hear and I see sparks, and I get a little scared, and all of a sudden my cheap screwdriver has been sort of welded to a heat sink. So I clearly touched something that had a buttload of current going through it that melted some of the heat sink and allowed it to try to weld itself to the screwdriver I was using. So I almost died. That was enough heat, clearly. I mean, enough amperage clearly to have killed me. But either way, luckily I'd gotten it done. I basically soldered the same, the replacement capacitor back in, and the TV works beautifully. And even now it still works. Not only that, like, since then, I've had probably 6 other major items in my home go to crap, and every one of them has been a failed capacitor. So it turns out there's anything with electric motor, anything that needs to come on fast, all that stuff, those all require capacitors, especially electric motors. And they're not meant to be turned on and turned off, turned on and turned off by their engineering. So that's often a big thing that can be replaced. You just got to be very careful. I found it with my salt generator, or my chlorine generator that takes salt and turns it into chlorine for my pool. I actually found 5 of them that were out in my what was that? Oh, my HVAC unit. That's what it was. It had 5 built into one. So I replaced that. And then in 2 separate occasions, I've replaced starter capacitors on my pool pumps that really just, that's all they needed was that. And then the pool pump started working beautifully. After the second one I replaced, I had thought about that advice. Someone told me about not turning them on and off. So I turned it on, and I only turn them off now to, change the filters or do something like that. And I just leave them on all the time, the pool pumps. They don't use a lot of electricity, so it's not that bad. But that's one of the neat things that comes from studying physics, is you learn a lot of stuff like that. And you learn enough to get dangerous enough where you could die. So just be careful, people. You really do want to ground everything. That little circle at the bottom of your receptacle, in most cases, your receptacle has a little circular thing, and it's got a slit and then a long slit, and then it's got like an upside down mouth at the bottom. If it's the best, well, I prefer, let's put it that way, I prefer when electricians turn it upside down so that that little mouth is on top. That's because that's the one that goes to ground, and if anything were to fall and just hit on one of those terminals, it would be hitting on the ground one, and therefore not a big deal. And in fact, even if it bridged over and touched the other ones, it's just providing a path to ground from the other one. So I generally like that. It doesn't look as good aesthetically, so that's why a lot of people don't do it. But that's another useful thing for you to know. But anyways, that little hole there in your light receptacles, if you go to your circuit panel where the it's called a service entrance, where the electricity comes into the house, you'll see basically, if you could look at it, you'd see that all the wires that come from there all come to a central location. Then they run down the wall of your house, and somewhere near the meter box will be basically the end of a pole, and it'll have a clamp on it, and it'll have a wire tied to it, and the pole will be about 1 inch in diameter, and it'll be copper, and it's either 6 or 8 foot copper pole you have to just drive into the ground, and that's literally a ground. So that's another piece of electricity and electronics and circuitry stuff that you might be interested to know. So yeah, each of these houses have that, and that's what they're all connected to. So the good news is, if you ever have to connect something to ground to ground it, then you can connect to that little hole in the bottom of your light receptacle. So anyways, so that's what capacitors look like. This is what a board looks like. These little things back here you've already ran into in lab, probably. They're resistors. As I said, there's other elements in there. We're not going to learn too much about diodes, but you could. We have all the tools. Your book talks about them and stuff like that. There's NP junctions and PN junctions and NPN junctions and all that good stuff to make transistors. But as I said here, we're going to start by studying capacitors, and I'm actually going to do it in a quite different way than the book does. I'm just going to start off with the theory of capacitance. So let me stop sharing here while that takes forever. I want to start off not with capacitors as a circuit element, but instead capacitors in theory and how we work them. So let's start off by sharing my screen with you guys. Okay. Yes, I'm on the right page. I'm going to do share screen this time. I am going to use my iPhone, iPad via AirPlay, and I'll hit share. And it's going to tell me to download something I download just about every week. Yep, that's what it's doing. All right. Okay, now I can connect to it. This should come up in a second. There you go. Okay, so I've mentioned the quantity capacitance. So just for the record, that is C, which equals Q over V. Therefore, from a unit standpoint, you can see the units of capacitance have to be the units of charge divided by the units of voltage. Well, the unit of charge is in fact the coulomb, and then the unit of voltage is in fact the volt. So a coulomb per volt is the unit for capacitance, and that's actually defined to be the farad, which equals just plain F if you want to use a abbreviation. Okay. Now, the more typical things that you run into, because just like a coulomb is a buttload of charge, a farad's a buttload of capacitance. For instance, if you happen to ever see a 1 farad capacitor, ideally that will be seen with a conductive wire connecting the two terminals, because it is a two terminal device. It's got 2 wires coming out of it, or 2 screw heads where you can attach to something or something like that. They should be attached together with a wire, and that keeps it from just randomly accumulating charge. In fact, they're also called condensers, and that's sort of what they do. It's almost like charge just condenses out of the air onto it. So if you ever see a 1 farad capacitor that's not wired that way, you want to stay away from it, because it can literally drive enough current through you in a split second to kill you. So you just want to be very careful. So it turns out the more typical units that we use are the microfarad, the nanofarad, the picofarad, or maybe the millifarad in some cases. Okay, so that's it's named after Faraday. You can see Faraday. So that's kind of neat, you know, if you've ever heard of the guy Faraday, Michael Faraday, a brilliant scientist with little or no formal education, but all the brilliance in the world. So, anyways, that's what capacitance is, and our stereo typical capacitance is, like I said, 2 parallel plates. So, or I might even call it archetypal. That'd probably be a better word to use. But anyways, let's start off by attacking a charged plate and using it to calculate the electric field due to a charged plate that's what we're going to assume is infinitely large. Now, what infinitely large means from a physics and mathematics standpoint is that we're going to examine places near this plane that are closer to the plane than they are to the edge by at least a factor of 10. Okay, once you start getting into less than a factor of 10, or even right at a factor of 10, all bets are off. But ideally, it'd be better even if it was a factor of 100 or more, but at least a factor of 10. So I'm going to start off with a typical scenario. I am going to draw a coordinate system. Let's say right here. I'm going to let that be my z-axis. I'm going to let this be my x-axis. I'm going to let that be my y-axis. And I'm going to try to center it up a little better. Actually, you know what? I probably need to move this over, because this is a diagram that I'm going to have to use by the center of it. So I'm going to come down here, put it right about here, and then like that. Okay, that's a little better. So now what I'm imagining is an infinite plane that looks like this. Which is clearly not infinite, but the point is, it just needs to be really big compared to what it was, compared to how far away from it you are. I think that looks about right there. Okay, so now to represent its infinityness, I'm going to say, and I'll do it over here as well. And I think that's sufficient for what we're doing. This is going to be my x-axis. This is going to be my y-axis. And this is going to be my z-axis. And I use this particular orientation specifically because it lends itself easily to the use of cylindrical coordinates, which I've discussed a little bit. And again, I'm not expecting you to know cylindrical coordinates, even though it's literally just a z dimension added to polar coordinates, which you are supposed to know. But again, that's not the key point. It's just me being able to use the language of it to familiarly speak about directions and unit vectors and things like that. In case you've forgotten, the way cylindrical coordinates work is basically we have x, y, and z. There's your x-axis, there's your y-axis, and here's your z-axis. And basically what you can figure is if I come over this far from the y-axis and this far from the x-axis, I'll make a dot. And then if I go up vertically that amount, then that quantity right there will be z. This quantity right here will be x, and this quantity right here will be y. And this point will be called x, y, z. But it could also be, it could also be r, theta, and z. Okay, so that's the main thing. So when you think of that, r is you can sort of think of as a line. Actually, let me make that a little clearer. That doesn't look that good, does it? Actually, this doesn't look too good either. Makes me mad. Okay. So what I'm gonna first draw is this line right here, and what I'm gonna draw here is this line and this line, and this distance from the origin to the point directly below XYZ, that distance is R. So if you're using spherical coordinates, that means you have a unit vector that points only in the XY plane, but points away from the origin. So in this case, it would literally point parallel to that black R line, only it points from the origin out towards us instead of back towards the origin. And then you'd have a theta hat vector that would in fact, I can actually draw it on here. Let's do this. So that's my R hat vector. Notice it only has, in fact, I can say cosine theta I hat plus sine theta j hat. That's actually what it is. And then 90 degrees ahead of that is the theta hat vector. And then, of course, straight up and down is the k hat vector. So that's the whole reason I use these coordinates, is it gives me access to r hats, theta hats, phi hats, k hats, all that good stuff. So that's what we're using here. Now, what I'm going to do is I want to assume that this plate, this infinite plane, has a very uniform charge density, and that uniform charge density is going to be called sigma. And for the record, I want to remind you that dq can equal lambda dl, or it can equal sigma dA, or it can equal rho dV. And in this case, what we're doing is we're saying sigma is actually equal to dq over dA. So that's the charge per unit area is the main thing I'm saying. Okay, so if it was an actual finite plate, you could take the total charge Q that it has and divide by the area, And if it's uniformly distributed, that's the uniform charge density. And in fact, every square inch, every square centimeter, every square millimeter, every square micrometer will have the exact same charge per unit area. You just, of course, got to use the same unit. So if you're, doing a square micron, then obviously you've got to convert the square micron to square meters, and you've got to convert the coulombs to coulombs. Okay. All right. So that's what we're looking at. And what we'd like to do is we'd like to calculate the electric field out at point P. So what I'm trying to figure out is right here along the z-axis at point P, what is the electric field? So at P, E equals question mark. That's really what we're trying to figure out, okay? And we're going to use Gauss's law to do it. Now, Gauss's law, so let me write the problem down. Use Gauss's law delta V equals negative integral at E dot dl and C equals Q over V to compute the capacitance of a parallel plate capacitor. Whoa. So that's the real problem we're trying to solve here. Okay, so I'm going to say solution. Closed integral E dot dA is equal to Q enclosed over epsilon naught. That is Gauss's law. Okay, so that's what we're starting with. Now, what I'm going to do is I'm going to say, first off, let's make a hypothesis. And why I do that is I've found that this is sort of what the thought process I think should be for the most clarity in applying Gauss's law. So Gauss's law says the flux, the net electric flux out of any closed surface, that's why we put the circle on the integral, that net electric flux through a closed surface is always equal to the charge within it divided by epsilon naught. That's a really big deal, but we use it in a weird way. We're using Gauss's law, as I mentioned to you before, in such a way that if certain symmetries are present, then we can actually extract that electric field magnitude out of the integral on the left. And we do so in such a way that we essentially never really do formally go through any process of doing an integral on the left-hand side, but we might often, we might have to do one on the right-hand side. The Q over epsilon naught sometimes requires that. So what we have to do in order to find that magnitude of the electric field, we have to make a hypothesis about the direction and what variables the magnitude depends on. So we're looking for a hypothesis about the direction of the magnetic field and a hypothesis about what the magnitude of the electric field is going to depend on. For instance, is it going to depend on X? Is it going to depend on Y? Is it going to depend on Z? Or is it just going to depend on theta? Or is it just going to depend on R? Or is it just going to depend on Z? Now, what I can tell you is if we look along the x-axis, say, let's say we consider a charge right here. What we can see from our knowledge of electric fields that we've gained from Coulomb's law, we know that the electric field, due to that guy, if it's a positive charge, is actually going to point in that direction. But if we took a diametrically opposed charge equal in magnitude, which would be very normal since it's uniformly charged, then this would be the electric field due to that guy. And I think you can see in that case, the two Z components will be exactly equal, but the two Y components will in fact be opposite in direction, but equal in magnitude. Does everybody see that? Anybody have any questions about that? Let me put up the chat here. That's funny. I was just looking at Elron's post about the Mercedes symbol. So hopefully everybody sees that by the symmetry of it, these two electric field vectors will have equal but opposite y components and will have equal z components. So this would be enough for me to argue that clearly this thing is not going to have any y components, because for every point on the positive x-axis, there is going to be, I think I was saying y-axis, but I meant x-axis. I apologize for all that if I've been saying y all this time. Anyways, for each point on the positive x-axis, there's an identical reflective point or reflection of that point on the negative x direction, in the negative x direction. And since it's uniformly charged, it should have at that point about the same amount of charge. So those x components should cancel out. And in fact, those x components would be, for instance, like this and like this, which makes them look a little less right, until I lie, cheat, and steal to make the P look better. Okay, so there you can sort of see that they're not the same. Now I'm going to consider 2 points on the y-axis. So that one's like 3 blocks away. So I'm going to do this one at 3 blocks away as well. In this case, I'll use blue so we can see a little better. This is going to make an electric field this way. I'm trying to draw as parallel as I can to the blue dashed line, but obviously I didn't do that well. Okay. And this is going to make an equally large electric field due to the one on the negative side of the y-axis. So in this case, you can also see that we're going to have, for instance, a nice positive y component of the electric field due to the one in the negative, along the negative y-axis. But we're going to have, in fact, a equally large negative y component of the electric field. So you can see that that red vector and that green vector are equal in magnitude in opposite directions. So those are going to cancel out. So now we've made the argument, and hopefully I've convinced you that the electric field will not only not have a x component or a y component, it's also not going to have any dependence on x and y. Does that make sense? Y'all see why if the x was, say, if it was stronger, say at x equals 1 than it was at, say, x equals 0, then that would require the uniformness of the charge distributed on the plate to be not so uniform. Okay, so that's why. Now that we have that in mind, that tells me that the electric field is not going to depend on x, it's not going to depend on y, and therefore it can't depend on anything in the xy plane. It's only going to depend on, in fact, the remaining variable, which is z. So I'm going to say E, the electric field, oops, wrong color. E, the electric field, dang it, why is it doing that? Let's see. Okay, got it right this time. Ooh, I'm so smart. E, the electric field, is going to be equal to E of Z K hat for Z greater than 0. And then it's going to be negative E of Z K hat, meaning that it actually points in the negative Z direction for Z less than 0. That's my big hypothesis. Okay, that the electric field's magnitude only depends on Z, the vertical distance away from the electric field, and that it points above the plane, away from the plane, assuming the sigma is positive. But when we get the answer, we're probably going to find that the answer for the magnitude of the electric field is proportional to sigma. So if sigma turns out to be an actual negative value, it'll automatically flip the vector backwards and everything will be good. So right now we're saying the electric field for z greater than 0 is in the positive z direction, and for z less than 0 is in the negative z direction. Okay. So how do we do this? Well, what we have to do is find a Gaussian surface. Okay, and there's nothing special about a Gaussian surface except we're using it for Gauss's law. And if we're using it for Gauss's law, we need each of the surfaces to have either the electric field be a constant on the whole one part of the whole surface, or the electric field be exactly perpendicular to one part of the surface. Turns out those two are actually the same requirements. Or the electric field has to be actually perpendicular to the area vector of the remaining sides. So remember, there's an area vector that represents any kind of area in space. And when it's a closed object, there's no ambiguity in which direction it points. It's going to be perpendicular. The dA vector is always going to be perpendicular to the actual area. And if it's a closed object, it's going to point as if it came from inside the closed in area out towards the outside. So there's no ambiguity on that. So can anybody think of a surface? Don't necessarily have to think of a particular shape, but can you describe a surface on which the electric field would be a constant?
Permanent magnet.
What's that? I couldn't hear you. I'm sorry.
A permanent magnet.
Yeah, with a permanent magnet, you could do that because that's going to create all sorts of issues. But yeah, you have a magnet. But I'm looking for more like, are you looking for a flat surface? Are you looking for a spherical surface? Are you looking for a bent surface? That kind of thing. So if I tried to make a Gaussian surface like we did on Monday of last week, it would be, usually the scenarios are what I call it a Gaussian pillbox, but I also called it a soup can. Or would it be a cylinder, which is also a soup can, meaning a cylindrical can, basically. So just the outside walls and the top and the bottom. Or would it be spherical? Any of those look like they'd have a constant electric field? Or can anybody think of a plane in this three-dimensional space I have drawn here that would give you a constant electric field everywhere on it?
The capacitor.
So, oh yeah, actually that kind of works. So yeah, if you actually drew sort of the shape of a capacitor, you could get that. So here's what I'm going to do. I'm going to draw the shape, and that's okay that many of you didn't necessarily see this, but now what you know is whenever you're dealing with a plane, you're going to have to use this Gaussian surface. Okay. We've already done it before, but it's been literally a whole week since I covered that material, so I completely get it. So what I'm going to do is I'm going to change my color to green, and I'm going to draw a Gaussian surface. Let's say like this. And it's actually supposed to be circular, but I'm drawing it in 3 dimensions. Actually, that didn't turn out so good. I'm drawing it in 3 dimensions, so I got to draw it elliptical. So what I'm going to do is say like this, like that. Okay. And then the side of it will come down and run into the surface, the charged surface. And then it'll intersect the charged surface. Whoa. It'll intersect the charged surface right along that space. And then down here, it has to continue because it's got to be a closed surface, right? So that's our Gaussian surface. I don't know why this particular line came out so, oh, it made a rectangle. That makes perfect sense. It doesn't really. I'm just being nice. All right, so let me try to go back and reconstruct this a little bit. This is clearly a blue line there. This is clearly a green line here. So and then my Gaussian surface should be something like that.
Why would the bottom of the surface not just be at the origin? Why would it continue down into the negative?
Because if I
Part
just
of the
stop
point.
it at the origin, it's not going to have any charge inside of it. Remember the way charges work on a conductive plate, which is what this is that all the charge will reside on the outside surface.
Okay.
So in order for me to actually get the charge, I'd have to go all the way to the actual surface. But then when I get there, I'm either going to land in a spot where there's no charge, or I'm going to have to go over past the other side and get the charge that's on the other side. So what I'm ultimately going to have is the total charge in the middle. The other thing is, this is also one of those scenarios where it's sort of like you just have to do what I do until you get in a better place to understand why I'm doing it. So right now, what you want to think is, okay, whenever Mr. Younger or I am trying to do a Gaussian surface for a plate, then I clearly want to use a soup can like this, and I want it to go from above the plate, through the plate, and then below the plate. You're going to see why in a second, what's going to actually happen that helps us in a second. Okay. So there's our Gaussian surface. It's not the best, ideally the ellipse in the middle and the ellipse in the top and the ellipse in the bottom should all be parallel. They're not, but that's close enough. I think you can get it. The main thing that you need to see, though, is that the differential area elements in the E dot dA have very specific dimensions or directions, if you will. So for instance, I'm going to say there exists a dA top, which I'm just going to label as DAT. Now in cylindrical coordinates, that would be RD theta. Okay, that would actually be what the differential area element is, but you don't have to use it. We're not going to integrate the left side, okay? But the key thing we are going to have to do is we're going to have to realize that on the top surface, the dA vector has to point perpendicular to the surface. So that's either up or down, and it has to point as if it came from inside of the surface and is leaving it. So that means it's got to be down. It's got to be up. So that's dA top is dA k hat. Also, there's a dA bottom, which I'll just label DAB, and that one's going to be negative DAB k hat because that one's got to point down. Now, if we stop talking about this as a pill bottle, which is what we've always done, we're going to have to talk about it as a soup can. So in this case, I'm going to say dA soup label is equal to dA soup label. Now, in this case, what we see, if I take one particular case, for instance, let's take this little bit of area right there. Everybody see that little area? Well, that little area is associated with this R and this change in theta. So we can let R be the radius of the soup can, and theta initially will be out to the left-hand side of that pizza slice. And then d theta will be from the left-hand side to the right-hand side of that pizza slice. But all we care about is a little rectangle on the end. Okay. And that means that the differential area element has to point out this way. So this is dA soup label pointing that way. This is the whole reason why I chose to show you again what the cylindrical coordinates were and what the unit vectors are for cylindrical coordinates. Does everybody see that dA soup label should be dA soup label times R hat? You see that that fits the description? Any questions on it? Okay, so meaning it doesn't have a Y component, it doesn't have a K it doesn't have an X component, it only has the electric field doesn't have a Y component. The electric field doesn't have an X component, and it's only got a K component, but the differential area element only has an X component and only has a Y component. I shouldn't say only, it has an X component and a Y component. But for instance, if I took the dA to be right here, in that case, it only have an X component. And if I took it to be right here, in that case, it would only have a Y component. That's what I was trying to get at by saying all that. So, so that you could recognize it is actually this R cosine theta I hat thing. So now I can say left-hand side. Well, that I could if it stopped turning into an eraser. Let's say left-hand side. And I mean left-hand side of Gauss's law. Now notice Gauss's law is not the kind of equation we've been using in the past where, you know, a variable's been solved for and we just throw in all the numbers and solve for one of the variables, or ideally we just have it already solved for the variable and throw in the numbers. This is one where we got to work out part of the left-hand side, we got to work out part of the right-hand side, then we got to set them equal to each other, and then we got to solve for part of it. That's why I take the time to write left-hand side, right-hand side, and all that stuff. So it's really the neatest way I could come up with to do it. So the closed integral of E dot dA, to satisfy the circle on the integral, that has to be an integral of E dot dA top on the top surface plus the same integral on the bottom surface plus the same integral on the soup label surface. Okay, so that's what the left-hand side's got to be. If I don't do each of those three surfaces, then I don't have an actual closed surface and Gauss's law doesn't apply. All right. Anybody have any questions before I move on with this? Okay. I'm checking the chat. All right. So I'm going to go ahead and deal with the top one. So I'm going to go integral of, now I look at my hypothesis E, and I see that the top surface is for Z greater than 0. So I'm going to say the electric field is E of Z K hat. And then I'm going to dot product that with the dA for the top, which was dA top K hat. Okay. Now, and that's all an integral over the top. Now I'm going to say integral over the bottom. This one's going to be negative E of Z K hat dotted with negative dA bottom K hat. Okay. And then the soup label part would be plus integral over the soup label of, now I got to be kind of crafty here. I've got to write plus or minus E of Z K hat dotted with dA soup label R hat. Does anybody understand why I had to write plus and minus E of Z in that soup label integral?
Because it's a circle and it's on the axis, there's the two parts.
Yeah, I think you're getting at it when you said the two parts part. That sounds like you're getting it. Our hypothesis said that for Z greater than 0, it would point in the positive K direction, right? And then for Z less than 0, it's going to point in the negative direction. So I had to account for both of those because I'm really going to integrate like from negative Z to Z, where Z is the distance away that the top of the soup can is. So in fact, Z is going to vary over that whole soup label surface from negative Z to positive Z. That means the electric field is going to vary from E of one particular Z to all the way to the E of the other particular Z. That means it can be positive, it can be negative. So that, yeah, that's what's going on there. But luckily, all that complexity isn't quite as bad as it could be because the dot product, K hat dot R hat, remember, is going to give me 0. So what I'm going to write here is this is all going to become the integral over the soup label of plus or minus E of Z dA soup label times K hat dot R hat. But K hat dot R hat, does anybody know what that will be? Anyone? Okay, so K hat is in the Z direction. If you look up where I wrote that R hat, that's cosine theta I hat plus sine theta J hat. So if you take a dot product of a vector with only a K hat and take that vector and dot product with a vector with I hat and J hat, but no K hat, then you're going to get 0. Another way of thinking of it is K hat has a magnitude of 1, R hat, again, it has a hat on top of it, so it also has a magnitude of 1. And then you're going to take the cosine of the angle between them, which is 90 degrees, and of course the cosine of 90 is 0. Okay. All right. So now that I've handled that particular part, I'm now going to say E of Z integral dA top K hat dot K hat plus plus E of Z. Notice the minus and the minus that I have here. In this particular part right here, there's a minus E of Z and there's a minus dA K hat. That minus and minus gives us a plus, and I get dA bottom K hat dot K hat again, but K hat dot K hat is just 1. And K hat dot K hat is just 1. And in fact, if I take the time to call this area down here A, then I can realize that the right-hand side of this equation, or excuse me, the left-hand side of this equation is in fact 2E of Z times A. Because this one is just A, and this one is just A. Okay. Now what I'm going to do, just to keep this from looking so confusing, I'm going to use this putrid pink color, and I'm going to draw a line in here to try to keep what's separate. There you go. All right, so that's the left-hand side. Now I'm going to go back to the right-hand side, and the right-hand side in this case is actually, hopefully it's going to be very easy for you guys. There's still some people that are having some difficulty with this, so I get it if you don't get it, but we'll get there. So the right-hand side is Q enclosed over epsilon naught. I've told you that the charge is sigma. That's the charge per unit area. So anybody think they can tell me what Q enclosed is going to be for this particular closed Gaussian surface? I want to reiterate that I did show you this for a very specific reason. Hopefully that'll help you.
Is it just sigma?
It's close because you have to have something with units of charge. Can this equation that I just showed you, can this one tell you how you get charge using sigma?
Times the area of a circle.
Exactly. And which is exactly what A was in the right hand, I mean in the left hand side that we just worked out. Did you get that? So let me make sure I got blue. So this right hand side is just going to be sigma A over epsilon naught. That brings us to left-hand side equals right-hand side territory. And what that means is I'm going to set 2e of z, which I can now drop the z if I wanted to, is equal to sigma a over epsilon naught. And you can see immediately that the a's cancel out. And ultimately what I get is E is equal to, again, going back to my hypothesis, sigma over 2 epsilon naught k hat for z greater than 0, and negative sigma over 2 epsilon naught k hat for z less than 0. So that's the electric field. We've now completed step one, or half of step one. And actually it's maybe 7/8 of step one. Everybody follow how we did that? This is exactly like a problem we did on Monday, but again, it's been a whole week, so I get you. We had a weekend and all sorts of good stuff. So everybody follow how we did that? Notice also that by the Gaussian surface going completely through and to the other side of the plate, we ended up getting an electric field popping out. So we got a positive term on the top and then an electric field popping out downward on the bottom. So we get another positive term on in the integral. So that combined gave us the 2 epsilon naught in the denominator, which is a very important point because we've tested that kind of thing experimentally over and over and over again. Now what we got to do is, now that we've figured out the electric field near a plate, in other words, or at least in any distance from an infinite plate, we now need to take a positively charged plate and put a identically negatively charged plate next to it, some distance d apart, and calculate the electric field between them. And then we're going to have to use our delta V equals negative integral E dot dl to calculate the voltage difference between them. So everybody sees that the electric field is sigma over 2 epsilon naught, pointing up above the plane and pointing down below the plane. Of course, if sigma is actually a negative charge per unit area, then they're going to point in the opposite directions. But this is a positive plate, so we're pretending the sigma is positive, so we're good to go. So now I'm going to draw a parallel plate capacitor. And here's our parallel plate capacitor. I'm going to suggest that the parallel plate capacitor is about one of those little blocks apart. And I'm going to draw this up here. And draw this up here. So there's our 2 plates. Like that. Okay. Let's say their distance between them is d. Let's say this one has a positive sigma charge per unit area, and this one has a negative sigma charge per unit area, and both of them have an area A. Okay. Now let's look at it purely in profile. So what I'm going to do is say I'm going to look from the side, so all I see is a plate here with a plus, 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 and a plate here. I'm obviously zooming in. That's why it looks so much farther apart now. With a plate here, minus, minus, minus. Okay. Now, I want you to tell me in the space between these plates, in which direction is the electric field due to the positive plate point. So I write E with a superscript plus on it, and that just means the electric field due to the positive plate. So pretend the negative plate's not even there, and tell me which direction does the electric field for the positive point, for the positive plate point in there. To the right, to the left, to the up or down, or in the page or out of the page. And Helron said to the right, and he's absolutely correct. Now, can somebody tell me which direction the electric field due to just the negative plate by itself points? Again, left, right, up, down, into the page or out of the page. Remember, the electric field direction is defined to be the direction in which a positive charge would like to go. So a positive charge, of course, is attracted to negative charges, and it tries to run from positive charges. So anybody have an idea? So yeah, with the negative plate, which direction should the electric field on its left point? Yes, I did say negative plate. And you're right again. So between the plates, the two fields add together to give you E total is equal to sigma over epsilon naught, not sigma over 2 epsilon naught, because it was two of those. There was sigma over 2 epsilon naught plus sigma over 2 epsilon naught. That's like 1/2 of sigma over epsilon naught plus 1/2 of sigma epsilon naught. So it gave us sigma over epsilon naught. Now, can someone tell me in which direction the electric field due to the positive plate points over here on the right-hand side?
To the left.
The positive plate. So remember, we're forgetting about the negative. The positive plate to its right purely points to the right already, because we've seen that this one little one already points to the right. And what we found on this page was that if we're on one side of it, it points up. And if we're on the other side of it, it points down. So in this case, if the sigma is an actual positive, it's going to always point away from the plate. So for this one, the electric field for the positive plate, even over here to the right, should point to the right as well. Do you see what you might have missed? Everybody's sort of, and that's normally the answer. People will think it points to the left. But remember, it's the electric field's direction is the direction that a positive charge would want to go. And to be honest with you, if you walk up to, let's say you walk up to a skyscraper in New York, or maybe let's say the Empire State Building, when you walk up to it so that your nose is maybe 6 inches away from one of the exterior walls of the Empire State Building, if you move back 6 inches, it doesn't appear you got any farther away from the Empire State Building because just more of it's visible. That's sort of the same thing that's happening here, because this doesn't have any Z dependence. It doesn't have any dependence on how far you are away. So really what's going to happen is the electric field's always going to point, in this case, away from the positive plate. So if I put a positive plate over there where I drove that arrow, clearly ignoring the negative plate means the positive plate is going to push positive charges off to the right. Now, you can use all those same arguments that I just did about the negative, about the positive plate. You can now use them about the negative plate as well, on this right-hand side. Remember, you're completely pretending like the positive plate is not there at all. And you're just saying, hey, if I put a positive charge right there where I wrote E negative on the right-hand side, which direction would that positive charge try to go? You're right, Elron. Anybody else have an answer? It's a negative plate, and it's just a plate. It's in case that's what's going on here. That blue line is the plate. We're looking at the edge of the plate. So there's nothing but air over here to the right. So in fact, what's happening is this electric field due to the negative plate points that way. And in fact, both of them have the same magnitude, sigma over 2 epsilon naught. So over here, I got E total equals 0. Now we got to do the same thing over here on this other side. What about E positive here? And what about E negative here? So in which direction would the electric field due to the positive plate point over here on the left?
The left.
Exactly. Because it's going to try to get away from the positive charges. How about the electric field due to the negative plate? Now completely forget about the positive plate and just think, what's the negative plate going to make a positive charge do right there where I wrote E negative?
Go to the right.
Go to the right. So you see in this case, they cancel out as well. And we'd say E total outside is equal to 0. All right. Now, let's revisit this because we're now in a position where I can do step 2 of our paradigm. Remember, step 1 of our paradigm is to use Coulomb's or Gauss's law to compute the electric field near a plus and minus charge configuration. Step 2 is use delta V equals negative integral of E dot dl to compute the voltage difference between the 2 plates. So what I'm going to do is I'm going to draw a coordinate system. Let's say right here, I'm going to draw a coordinate system that has, well, actually, I don't want to do that part. I'll leave that off for right now. And now I'm going to say this right here. And now I'm going to turn off it making pretty pictures. And I'm going to say this is my x-axis and this is my z-axis. Notice I've got an entirely different x and z configuration and direction compared to the previous page. Okay. Now, what I'm going to do is I'm going to say the left plate, which is the positive plate, is right along here. Okay, so that's my positive plate. And then over here, I'm going to say this is my negative plate right here. And in fact, this distance right here is D. Whoa. Okay. And this is in fact a negative plate. Okay. Now, what I want to do is I need to use delta V equals negative integral E dot dl to calculate the change in voltage from one side to the other. My ideal scenario is I get a positive so I don't have to erase the negative. And in fact, it gives you good practice to actually work with it to see that you integrate it the right way. But in general, if you integrate from the negative plate to the positive plate, that should give you a positive change in voltage because the change in voltage is the final minus initial. And final being larger than the initial is what happens when you go from negative to positive. Okay. So I'm going to do that, but we got to remember it's a line integral. And that means with a line or path integral, we either have to let the range of integration dictate which way we're going, or we've got to let the DL dictate which way we're going. Once we decide on one, the other one has to be in the positive coordinate direction. So what I'm doing here is I am going to imagine starting off right here at the negative plate and integrating this way. Okay. I'm going to say from, in this case, maybe I actually have a Z value that's not 0. It doesn't really matter too much, but I'm going to say from X equals D, Y equals 0, Z equals 0.2 to X equals 0, Y equals 0, Z equals 0.2. Oops. Like that. Okay, that's really what I'm doing. So now I'm going to calculate delta V, which is really V final minus V initial, is equal to negative integral of E dot dl. This is the whole reason we did that last part, was so that we know what the electric field is between the plates. Now, that being said, we see that it's a constant. You see it's sigma over epsilon naught. Both of those are constants. So I don't really have to use the sigma over epsilon naught. I can just call it E and that'll be fine. And that's what your book does. So I'm going to do the same thing. I'm going to say equals negative integral And now I'm going to say E times, now in this case, we can see that the electric field points from, it points in the direction a positive charge would go. So it actually points in the I hat direction. Does everybody see that? You see that in the diagram, the third diagram on the right there, you see that the electric field is pointing to the right and the path of integration is pointing to the left. Maybe I draw it on there too. Okay, so that's what that is. Now, here's my choice. If you want, some of you can do the opposite that I'm doing, and you'll see that you get the same answer. But I am going to choose the DL to decide which direction I'm going. Okay, so I'm going from right to left. So my DL should be negative DX I hat. Since I've now given my actual direction with the differential element, the DL, I am now going to put the range of integration from small coordinate to large coordinate. The small coordinate, you can see we're integrating over x, so the small coordinate is x equals 0, and the large coordinate is x equals d. Okay, now if you want to try the other way, what you're going to do is you're going to say, okay, well, I'm integrating from x equals d to x equals 0. That tells you, the integrand, exactly which direction you're going. Therefore, I now have to use dx I hat for my DL, because that has to point in the positive coordinate direction. So I think you can see mathematically it's got to come out the same, but that's the key point here. And you can also see, while in most cases you can't even tell the difference between a regular integral and a line integral. But that's actually a bad thing, because you get a lot of answers right even not knowing what you're doing. So now that I do that, I'm going to go ahead and say this negative that's with the dx and the negative that's out in front, that's just going to become positive. And I'm going to say the integral of E dx, and remember, E is a constant, times I hat dot I hat. Again, this is using the fact that the dot product is a linear operator. A dot product being a linear operator means I can pull all the non-vector stuff out in front of it and just let one vector act on the other vector. And that's what I just did. Can anybody tell me what I hat dot I hat is? Which looks like an excited owl now.
One.
Yes. The magnitude of I hat, since it has a hat on it, is 1. The magnitude of the other I hat is 1. And since they're both I hats, the angle between them is 0 degrees. So cosine of 0 degrees is 1. So yeah, we just get 1. And in fact, what we get is the E times the integral of dx from 0 to d. So you can see, oops, I shouldn't do it that way. You can see the answer is E times D. So that's our change in voltage. Easy peasy, right? Now the final step. C equals Q over V. Now, if I were to tell you, as I did in the drawing, that the area of a single plate is A, what would be the total charge of one of those plates? Ignoring the signs, in other words. Anyone?
Sigma times area.
Exactly. So we're going to put sigma times area there. And then V is just E times D. I'll write that, but now I'm going to take another step and plug in what we know E is. So I'm going to say sigma times A over. We know that the electric field is in fact sigma over epsilon naught. And oops, then I have the D next to it. So ultimately, I think you see that, notice the sigmas cancel out. That's the last thing that makes it refer to a charge. And as I told you, capacitance should never depend on the charge. It's a geometric quantity. So I ultimately get epsilon 0, which I should have put in a different color, epsilon 0 times A over D. And that is the capacitance of a parallel plate capacitor with air separating the two plates. So the final step, or the final answer, is epsilon 0 A over D. Any questions on that? Okay, so let's do an example real quick. So example. Well, I really hate this thing always turning into an eraser. Does it every darn time. Okay, so what I'm going to do is I'm going to say, what is the capacitance of a parallel plate, which I'll write PP, capacitor, because I just want to write the word PP in my notes. So what is the capacitance of a parallel plate capacitor whose plates are 20.0 centimeters by 6.00 centimeters and are separated dang it, by a distance of 1.00 millimeters and that bridges an air gap. In other words, the actual quote unquote dielectric between the plates is just air. That's going to be part A. Part B is calculate the electric field. And part C, assuming that D gets 100 times smaller, how big must A be to have C equals 1.00 farads? So there's your questions. What's the capacitance of a parallel plate capacitor whose plates are 20 centimeters by 6 centimeters and are separated by a distance of 1 millimeter, and that bridges an air gap? In other words, it's filled with air. Part B, what's its E field? And part C, assuming that D gets 100 times smaller, how big must A be, despite that, to get a 1 farad capacitance? So let's do our solution. So solution. First off, we know that area is equal to 20.0 centimeters times 6.00 centimeters, which equals 120 centimeters. That's 120.0. That gives you 1 extra sig fig. So I'll put it there. And that's centimeters squared. But in order to make this into square meters, which it has to be, I have to say 100 centimeters is equal to 1 meter, but that only gets rid of one of them. So I got to square that. So when I do this, basically I divide by 10,000. So this is 0.0120 square meters. So 1, 2, 3, 4. Yeah, that's right. So that's it converted to square meters. I've got D is equal to 1.00 millimeters, which is really 1.00 times 10 to the negative third meters. That helps. And I know that C is equal to epsilon 0 A over D. So I can now say C is equal to 8.85 times 10 to the negative 12. Remember, the units for this are coulomb squared per Newton meter squared. You can actually do that in terms of joules, and that might help you a little bit. Remember, a joule, or remember, a volt is a joule per coulomb. So you can take that Newton meter and still have a meter on the bottom, but that Newton meter becomes a joule. And then with a coulomb from the bottom, that's a joule per coulomb, which is a volt. So that can actually help you a little bit. But anyways, you should work out through what those units are. The A is going to be 0.01200 square meters. That obviously cancels out with the square meters in the bottom. And then I got 1.00 times 10 to the negative third meters. That puts another one in the bottom. So now I've got coulomb squared per Newton meter, which is a coulomb squared per joule. If I do this math, I'm going to say 8.85 e to the negative 12 times 0.012. Now I'm going to divide that by 1 e to the negative 3, and I'm going to get 1.062 times 10 to the negative 10th. And notice I said that's Newton coulombs per Newton meter, or coulomb squared. Okay, so we got rid of the 2 meters squared at the bottom. A Newton meter is a joule, so I can write this as 1.06 times 2 times 10 to the negative 10th. Now I'm going to say, take one of those coulombs that's at the top and put it as a coulomb in the denominator in the bottom. That'd be a Newton meter per coulomb, like that, which is in fact, do I got everything? It looks like it. It looks like coulomb squared. Okay. So this down here, Newton meters a joule. This is a joule per coulomb. So this is a coulomb per volt. So I'm going to write 1.062 again times 10 to the negative 10. And now that's a coulomb per volt, because this right here is a volt. And a coulomb per volt is a farad. So I can finally write it as 1.062 times 10 to the negative 10th farads. Now, if you wanted to, let's say, multiply by 10, I could make that 10.62, for instance. And if I made that 10.62, then that could work out a little better for me. So let's change it up a little bit. I'm going to say this is 10.62 times 10. So multiplying by 10 there means I need to divide by 10 on this side. So 10 to the negative 10 divided by 10 would be 10 to the, well, actually I multiplied that one. I should be divided. Actually, yeah, I think that's what I want. I multiplied by 10, I divided by 10. That'd be 10 to the negative 11. That's not very helpful. Actually, let me do a different way. I'm just playing with this to get one of the typical prefixes for SI. So for instance, I could divide by 10. If I divided by 10, then I'd have to multiply the 10 to the negative 10 by 10, and that would give me 10 to the negative 9. So that'll work. I can say 0.1062 times 10 to the negative 9 farads. So basically I divided the mantissa, which is the number, I divided that by 10, and I took the multiplier, the power of 10, and multiplied by 10, and that gave me 10 to the negative 9. And of course, you know, 10 to the negative 6 is micro, 10 to the negative 9 is nano, and 10 to the negative 12 is pico. So this is 0.1062 pico farads. Okay. Any questions on that? All right. So now that we have that, we can do part B, which, reminding myself, that's the E field. So there's a couple of ways you could do it. For part B, you can realize that V is equal to ED if you wanted to. And then you'd say, okay, well, if I knew the voltage, I'd be good to go. And that was the part I think I left out. Oh, yeah, I did. Sorry about that. Let's do this here. The C is connected to a 12-volt battery. Okay, so with that in mind, I could say, oops, should probably stick to blue. I could say 12.0 volts. I'm just going to pretend like I add that extra sig fig because I was using 3 sig figs and everything, is equal to E times D, and D is 1.00 times 10 to the negative third meters. So this gives me E is equal to basically 12,000 volts per meter, or E is equal to 1.20 times 10 to the 4 volts per meter, which you could also write as 12.0 kilovolts per meter. That would work as well. Okay, so that's one way you could do it. But there's another way you could do it as well. And that other way is basically E, darn it. It's basically E is equal to sigma over epsilon naught. The sigma, of course, is the charge per unit area. And I don't think I gave you enough to do that, did I? No, I did not. So I'll say and Q is equal, remember C equals Q over V, so Q is equal to C times V. So I can say C is equal to 0.1062 times 10 to the negative 9 farads. And then V is 12,000 volts per meter. Oh, nope. Sorry. I forgot we're talking about just V here. So V is 12.0 volts. When I do that, I can actually get the charge on them. And this is another calculation that you should be able to do. So when I do this 1.1602 times 10 to the negative 9 times 12, that gives me 1.274 4 times 10 to the negative 9 coulombs. That's 1.274 nanocoulombs. So that's something that's helpful. Now I can see that the electric field is supposed to just be E is equal to sigma, which is the charge divided by the area. So I can say 1.274 times 10 to the negative 9 coulombs divided by the area, which we found to be 0.01200 square meters. That's just my sigma. And now I'm going to divide that by 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. So I'll take that 1.274 times 10 to the 9th. I'm going to divide that by 0.01200. That gives me 1.062 times 10 to the negative 7th coulombs per square meter. That's my sigma. I should write that too here just so you'll know what I'm doing later. And that all will be divided by 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. And that gives me 12 or 12.0 times 10 to the 4 volts per meter. And in other words, exactly the same result we got before. Okay. So that was part B, and I did it 2 different ways for you. Anybody have any questions on that? All right. I'll do part C and then I'll give you guys a break. Assuming that D gets 100 times smaller, how big must A be to have C be a 1 farad capacitor? So we're going to say C, part C equals 1.00 farads, and C is also equal to epsilon 0 A over D. But this time I'm going to say D2 is equal to, remember we had 1 millimeter, so it's going to be 1.00, but instead of times 10 to the negative 3, it's going to be times 10 to the negative 5 meters like that. And what we want to know is A equals question mark. So I'm going to say 1.00 farads is equal to 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared times A over 1.00 times 10 to the negative 5 meters. And this gives me A is equal to, I'm going to take 1 and multiply it by 1 times 10 to the negative 5th, which obviously is 1 times 10 to the negative 5th. And then I'm going to divide that by 8.85, 10 to the negative 12th. And that gives me 1.130, carrying 1 extra sig fig, times 10 to the 6 square meters. Now, just to let you look at this, if I took the square root of that, that is basically 1,063 meters by 1,063 meters. So we're literally talking more than a kilometer on each side. So as you can tell, obviously making a 1 farad capacitor is not necessarily a trivial feat with our technology, because it looks like it must have a huge area to get such a capacitance. But in fact, there's actually our tricks. For instance, we can use, if you talk about surface area, we can use carbon and carbon as a fine grained dust actually gives you area that's equivalent to the little surface areas of the little dust particles added up, so you can get a lot more bang for your buck, stuff like that. But anyways, that's roughly what area it'd have to have. Even though we made it 100 times closer, we literally made it down to 10 microns. That's how close the two plates are, and still the area was ginormous. Now it turns out we can go from C equals epsilon 0 A over D. We can go from that to C equals K epsilon 0 over D, A over D, which also equals epsilon A over D. And that's by adding a dielectric. Okay, that was horrible writing. I apologize for that. I'm going to write it better now. But anyways, you can go ahead and take it's 7:11 right now. Let's be back at 7:20. So I'm here if anybody has any questions. I'm just going to rewrite this real quick so it looks a little better. Now, what you will see is when we do add a dielectric, it's only like usually a factor of 4 or 5, maybe you can get up to 6 or 7. So that's not the answer to trying to make a 1 farad capacitor. I'm here if any of you have any questions. I'm actually double checking my calculations because I just looked at an example I did before. Actually, I looked at the example in the book, and it worries me how different mine is from the books, even though I used my own numbers. So I'm checking that out while you guys are on break. The area is supposed to be 20 times 6. It gives me 120, and then I'm going to divide that by 10,000. That's 0.012. I got that. And I got the same thing, 1.062 times 10 to the negative 10th, so that's good. Nanos 10 to the negative 9. Could have made it 10 to the negative 12. Yeah, that's what I could have done. What I instead did, I actually called that a picofarad. That's supposed to be a nanofarad. That's what it was. I was looking at the wrong prefix. Got about 4 more minutes, everybody. This has already been corrected in your notes. So you can see the pico was supposed to be a nano. And I even did a conversion for it to picofarads. It'd be 106.2. And of course, a 2 is not a sig fig. Put that there. I'm going to go ahead and draw our next setup. All right, it looks like it's about time. So we're starting up another problem. In this case, I'm doing what's called coaxial cable. So if you guys have like DirecTV, Dish Network, or Time Warner Cable or any cable company as well, you will have wires running from somewhere outside of your house into your house. You might be running them up to a satellite dish in the case of DirecTV or Dish Network, or to some center in the case of a cable company. But the coaxial cable is this really sort of thick looking, nice looking round cable that you'll see poking out of walls or screwed into jacks and walls, and then it'll come into the back of your cable box or your DirecTV box. But if you were to look at them, they have an end on them, and the end is normally silver and has threads. Sometimes they don't have threads, but they're normally threaded. But if you look in there with the end on it, what you'll see is some white material. And then in the very center of it's a little thin copper wire. And I say thin, it's probably 3/4 of a millimeter in diameter, something like that. So not huge, but also not completely small. It's not that easy to break, for instance. Now, if you were to pull off that that end, which is the it's normally a chrome or gold with some threaded parts. If you pulled that off, what you'd see is actually like a little copper wire in the center, the same copper wire we just saw, with some sort of white filling all around that. And then outside of that will be basically what looks like aluminum or maybe stainless steel braided screen. Like it looks like screens from a back porch, but it's braided around that white filling. And then outside of that is usually a black rubber. So that inner part is an inner conductor, and that outer part with that screen looking stuff, that's a conductor as well. So a typical scenario would be like this coaxial cable, and this coaxial cable, for instance, would have a inner charge for a particular length, let's say an inner charge of Q, and the outer charge for the inside edge of the screen would be negative Q. So what we're going to try to do is we're going to try to do our three-step paradigm. Step one, Gauss's or Coulomb's law. Step two, delta V equals negative integral E dot dl. Step three, C equals Q over V to find the capacitance. And in this case, it's going to lend itself to finding the capacitance per unit length of wire. And in fact, if you're lucky, you can occasionally pick up RG6, and I think the other one's RG57 or something. I can't remember the number. RG59 is, I think, what it is. But printed on the outside of the coaxial cable will be something like a certain number of microfarads per meter or something. That's when they're actually giving you all the details. So what I've done is I said the inner conductor has a radius of R sub A. The outer conductor has an inner radius of R sub B. I'm going to pretend like a length L, let's say a length L of the inner, wire has a charge plus Q, and the outer minus Q. I want to know C equals question mark. Okay. So again, I'm going to use a Gaussian surface. I'll do it with a green shape again. In this case, I'm going to say roughly, well, evidently I'm just going to pick up stuff at random and draw it by accident. Okay. So I'm going to say like this. What I'm trying to choose is a surface again on which either the electric field is constant, which is also consistent with the electric field being parallel to the dA vector, or it's going to be perpendicular to the dA vector, in which case you get a integral that works out to be 0. So that's the scenario we're shooting for. I don't like the way this one leg turned up, so everything else looked pretty good, but not that. That's like that. And now I got to fix this. Okay, that was pretty good. Okay, so there's my Gaussian surface, and I'm going to say that Gaussian surface has a radius of little r, where little r is in fact, little r is in fact less than RB but bigger than RA. So solution. First off, RA is less than little r is less than RB. And closed integral of E dot dA is equal to Q enclosed over epsilon naught. Okay. And I didn't explicitly state it, but I am telling you that this coaxial cable is uniformly charged. So let me go ahead and do that right now. I'm gonna write it on here so no one think. So uniformly charged. And what that means is if you take the charge that any particular part of it has and divide it by the length, and you use the same units for charge and length, from one measurement to the next, you'll always get the same number of coulombs per meter. That's what uniformly charged means. I'm going to say that this Gaussian surface, in fact, has a height L, which happens to be the same L that we used a second ago. So that's where I'm going with this. Again, in this case, we have cylindrical symmetry, and we're using a soup can or a pill bottle, which are pill box. So that's the normal scenario. When you have a plane, you use a cylinder. When you have a cylinder, you use a cylinder. But you'll notice that the important surfaces are different here. So I'm going to say hypothesis. What I know from Coulomb's law, remember we did that the very first day in chapter 21, we did the Gauss's law, or excuse me, the Coulomb's law in integral form, and found that the electric field due to an infinitely long line of charge was lambda over 2 pi epsilon naught times r. That's what I'm using as my idea. I know that this has cylindrical symmetry, and if it really is infinitely long, I'd expect E, the electric field, to depend only on the cylindrical radius R. So I will not subscript it. I'm just assuming it's the cylindrical radius. And in fact, it will point in the cylindrical R hat direction. So both of these R's are related to cylindrical coordinates. So that's what I expect the electric field to be like. Now, on the top surface, we have dA top is going to be just a dA k hat. On the bottom surface, dA bottom is again going to be a negative dA k hat. I'll put a B on there and a T on there. Technically, the dA and the DAT and the DAB would both be the same. And in fact, they'd be RD theta if we were using cylindrical coordinates. And the dA soup label, DASL, would in fact be DASL. Actually, I don't like how that turned out either. Would be dA soup label times, in this case, it's going to point in the R hat direction again. So I'll just put an R hat there. So for this one, it would actually be RD theta. That's the width of the rectangle. And the height of the rectangle would be DZ. So it'd be RD theta DZ or RDZ D theta. But again, we're not doing integrals on the left-hand side. That's the whole point of Gauss's law, is we're extracting the, at least in using it this way, that's the whole point of Gauss's law, is we're extracting the electric field by not integrating. So let's go with the left-hand side. I'm going to say left-hand side, the closed integral E dot dA. Now, again, this means the integral of E dot dA over the top plus the integral of E dot dA over the bottom plus the integral of the soup label, again, of E dot dA. Okay, so this is, which I'll put right here, just to say that I'm still continuing the left-hand side. I'm going to have the integral over the top. Now, in this case, over the top, the electric field is going to be E of R. Now, that R is variable, okay? And it points in the R hat direction, but the dA is going to be dA top K hat. So yeah, the E of R is going to vary because I'm going to go from R equals 0 to little r. And it doesn't matter anyways, because even though that's going to vary and it would make it harder to integrate, the r hat dot k hat is going to give us 0. So that one's going to fall out. Now I'm going to do the same integral for the bottom, and that's going to again be E of R hat. In this case, it's going to be dotted with negative dA bottom k hat. So that one's going to give us 0 as well. Plus, I'm going to do the integral over the soup label of E of R. Now, in this case, on the soup label, the R is actually a constant. So E of R is a constant. So we have E of R hat dotted with, now we're going to say dA soup label R hat. So this guy is going to become the integral of E of R dAt R hat dot K hat, which is 0. This one's going to get integral E of R dA, and technically it'd be a minus there, dA bottom, and then it'd be R hat dot K hat, which again is 0. But this other guy is actually going to turn into something useful. It's going to be E of R, because again, we're integrating on a surface, and this surface is defined such that R is equal to a constant because we're doing the soup label part. Therefore, it's a constant. It can come out in front of the integral, and we're ultimately just going to integrate dA soup label and multiply that by R hat dot R hat like this, which works out to be, of course, 1. Now, the integral over the soup label is literally just the area of the soup label. So if I took that soup can label and pulled it off, or let's say, imagine cutting that soup can's label straight down one side, like right on that little black line, it would make a shape of a rectangle. Can everybody envision that or see that? If that's the case, how wide is that rectangle? So we're cutting like right along here, and I'm asking you, how long is this rectangle that comes all the way around and comes back to here like that? Can anybody tell me how long that is? Because this one's going to actually depend on R, so I have to have the actual area. I can't just use A like I did before, because that A depended on R, but that E of R did not depend on, or excuse me, that E of Z did not depend on R, so I didn't have to put a formula for it. So how wide would that rectangle be? Anyone?
2 pi r.
Exactly. And how tall would that rectangle be?
The length L.
Exactly. So the left-hand side becomes, as I argued before, it's always an electric field times an area, maybe plus some zeros, or maybe plus another electric field times an area, but that's always what the left-hand side is supposed to be. If you get something different, then you know you've screwed up. So this is E of R times 2 pi R times L. That's the right-hand side. Now, I worded the question very specifically, so you should be able to answer this right-hand side question, but the right-hand side of this is Q enclosed over epsilon naught. So who can tell me what Q enclosed is going to be?
Plus Q.
Exactly. It would normally be lambda times L, but we know from the description that lambda is Q over L, and we happen to use the same L. So yes, it's just plus Q over epsilon naught. So now I can say left-hand side is equal to right-hand side. When I do that, I get E of R times 2 pi R L is equal to Q over epsilon naught. And going back to my hypothesis, that suggests that E is equal to, let's write it this way. I'm going to say Q over L divided by 2 pi epsilon naught times r in the r hat direction. And that is the right answer. I wrote the Q over L just because you'll remember when we actually worked this before, I gave you the answer in terms of lambda. That's what Q over L is lambda. Okay, so now we have the electric field. We have figured out part A, or step 1 of the paradigm. Step 2 is I need to integrate. I'm going to take and integrate from here to here. So delta V equals negative integral of E dot dl is going to go as follows. Okay, I've got a negative here. I've got an integral. E is actually going to be Q over L divided by 2 pi epsilon naught R hat dotted with, now last time I used my differential length element to dictate which direction I'm going. This time I'm going to use my range of integration, okay, just to mix it up. So I'm going to call the DL to point in the positive coordinate direction, which I'm going to say is dr r hat. And then I'm going to integrate from RB to RA. And of course, you remember RA is the actual smaller one. So now I can, again, using the linearity of the dot product, I can pull out all the stuff in the front, and I can even pull stuff out of the integral because they're constants. So I'm going to write, I'm going to write Q over L divided by 2 pi epsilon naught integral of dr over r times r hat dot r hat. And again, hopefully everybody knows what r hat dot r hat is. It's 1. And this is from RB to RA. So ultimately, I just get Q over L 2 pi epsilon naught natural log of RA over RB, and I dropped a negative, which I shouldn't have, so that negative should be there. Now, if you'll notice, since RA is smaller than RB, the natural log of RA over RB is in fact negative, so I can say delta V, if I want it to be positive, I'm going to write this as Q over L divided by 2 pi epsilon naught times the natural log of RB over RA. So this is another important result. That's the actual voltage difference from one plate to the next. Now I'm ready for step 3, and step 3 is C is equal to Q over V. So what is Q? Well, for a length L, Q is just Q. So I'll just write Q up here. And then for a length L, we get Q over L over 2 pi epsilon naught times the natural log of RB over RA. And again, you see that the Q's cancel out, and I get 2 pi over 2 pi epsilon naught. Okay, because the 2 pi epsilon naught, basically when you divide by Q over L over 2 pi epsilon naught, that becomes the same thing as multiplying by 2 pi epsilon naught over Q over L. So this is actually going to be 2 pi epsilon naught L over the natural log of RB over RA. And that is the actual capacitance. In fact, you can divide both sides by L, and in doing so, you will get, by doing so, you will get the charge per unit length. Any questions on that? All right, so that's the process that you do for cylindrical symmetry. The three symmetries that we can use to solve the integral equation for the integrand are only infinite planar, infinite cylindrical, and spherical. So that's pretty much all you got to memorize. Is you got to remember, hey, if I'm using an infinite planar, then I need to use a soup can. And of course, the top and the bottom are the ones that are important. The soup label is going to go to 0. But if I use an infinite cylinder, then the soup label is the important part, and the top and bottom are going to go to 0. And then finally, if I'm using a sphere, then I need to use a spherical Gaussian surface, which I'm going to do now. So anybody have any questions on this? Because I got to fit in one more example before I let you guys go. Your book works all these examples, by the way. And one student asked me this, and it was a very good question. They said, my book doesn't show me doing integrals on the on the left-hand side. Is there some reason why you're doing them on yours? And I explained to them that I'm trying to show you exactly what's happening mathematically. I don't want you technically using all this stuff. I mean, if you're getting confused and it's the only way that makes sense, then I want you to use it as much as possible. But if you look at the book and you can then better understand what the book is saying versus just because of what you've seen with we showing you, you will probably find the book is a lot easier way. And that's okay. You can use that. Okay. It's not gonna take off any points or any of that kind of thing. But I'm trying to sort of tip my hand and show you, hey, this is the gory details that we're avoiding by doing the problems this way. So a couple things I want to point out to you. When you put one or more capacitors in series, it turns out that you can have, for instance, let's say we have a battery here. That's a symbol for a battery, by the way. And it runs into a capacitor C1 in series with another capacitor C2. Of course, you can do that for any number. Well, it turns out in that case that actually, let me draw the other circuit. This is exactly equivalent, meaning the battery will know no difference if you replace these two capacitors with this one capacitance, which I'll call C equivalent S for C equivalent series in series. And it turns out that the formula is 1 over C equivalent in series is equal to 1 over C1 plus 1 over C2 plus ... for however many of those capacitors you have. Okay. You can look up this on my YouTube channel. You can see it derived. You can read the derivation in the book. It's all pretty simple, but I just want to make sure you have the ability to use these two formulas. So another one can be gotten by taking a battery and putting it in parallel with two capacitors, C1 and C2. And again, this is one of those scenarios where you can do any number. This is exactly equivalent, according to the battery. This is exactly equivalent to one capacitor that we'll call C equivalent P for parallel. And the formula there is C equivalent parallel is equal to C1 plus C2 plus ... So that's the other formula that I want you to be able to use. I've already put plenty of examples regarding using these on the unit in Canvas, so you've got plenty of examples. What I want to quickly do is blow through a spherical charge distribution that's made into a capacitor. So let's imagine a sphere of charge plus Q in radius R A plus Q, and then outside of it is a spherical shell of radius RB and inner charge minus Q. Okay, let's actually make that a minus. That's what we're trying to calculate the capacitance of. Now, you can already hopefully think about the issues with this, is specifically how are you going to get into the thing in the middle. And that, of course, is a real issue, but it's something that we have handled, believe it or not. So these two are spheres. what we're going to do is we're going to take a Gaussian surface, which is also a sphere, and we're going to take it to be concentric with the other spheres, and its radius is going to be little r. And then we're going to take Gauss's law. So this is our solution. Gauss's law says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. So that's what we're using. I'm going to say my hypothesis is that E is going to equal E of R times R spherical hat. Okay. This means the spherical coordinates. Okay. And then my dA is just going to be dA R spherical as well. So the left-hand side becomes closed integral E dot dA is equal to the integral of E of R, R hat spherical, dotted with dA R hat spherical. And that's over a sphere of radius R, little r, which is between RA and RB. That's the key thing to remember here. So this ends up being, since I'm integrating it on a sphere of radius R, the E of R comes out and I get the integral of dA for a sphere. So I get E of R times 4 pi R squared, because that's the formula for the area, the surface area of a sphere. The right-hand side, excuse me, the right-hand side is again Q enclosed over epsilon naught, but we can see the only charge enclosed is the inner one, so that's Q over epsilon naught. Now I can say left-hand side equals right-hand side. And that gives me E of R times 4 pi R squared is equal to Q over epsilon naught. So with our hypothesis, we reached the conclusion that E is equal to Q over 4 pi epsilon naught R squared R spherical coordinates. And that's what our answer is supposed to be for the electric field. Okay. Now I'm going to integrate, and I'm going to do so from the outer surface, which is a negative, to the inner surface. I got about 1 minute left. So delta V equals a negative integral of E dot dL. I'm going to say this is a negative integral of Q over 4 pi epsilon naught R squared R hat spherical dotted with dr R hat. And I'm going to integrate from RB to RA. So I've chosen the coordinate direction, I mean the range of integration, to decide which direction I'm going. The DL just points in the positive coordinate direction. So when I integrate this, this becomes the integral of dr times r to the negative 2, which is negative 1 over r to the negative 1. So I get delta V is equal to positive Q over 4 pi epsilon naught. And then I'm going to say 1 over RA, which is a small number. So 1 over RA is the big number, minus 1 over RB. Like that. Therefore, I can say C equals Q over V just becomes Q over 4 pi, or excuse me, becomes Q over 4 pi epsilon naught. I can actually make this RB minus RA over RB. In other words, just getting a common denominator. And this ultimately gives me 4 pi epsilon naught. That comes to the top. The Q's cancel out. And the RB comes to the top, and I get RB minus RA. And that's the whole formula. So you've now seen the 3 examples of the paradigms that are possible with Gauss's law. All right, and you actually have all the tools you need, with maybe 2 exceptions to doing all the homework for chapter 24. That being said, I made it due. It's not supposed to be due till some time from now. I think it's at least the 14th. I might even have it set to the 30th right now, but I don't want you waiting till the 30th. I want you to start it immediately. So you guys are free to go. Let me know if you need anything. If you have any questions, go ahead and contact me. I will email you when I post my 2 practice tests, and I'll probably be posting the tests too as well. So they'll both be posted, and I'll email you when they are. Have a good one, and I will see you again on Wednesday. But again, I'm waiting for the last person to leave in case you have any questions. Thanks, Elron. See you later, bud.
I have one question. When is the homework chapter 23 homework due?
Let me pull it up real quick and see. I'm still here, so I got this. Let's say all assignments. Chapter 22 was actually due.
I said 23. Yeah, I know 22
23.
was due yesterday.
Yeah, and actually, in light of the questions y'all are asking me, I'm feeling y'all might not have got chapter 22 enough. I think I'm going to move that date back at least another 2 days. So let me go ahead and do that real quick. So if you missed it, it's no big deal. It's going to be pushed back. I'll push it back till Friday. So now chapter 22, I know you asked about 23, but chapter 22 is now due Friday, 11:59 on the 14th. And chapter 22 homework is the same way. Chapter 23, it's currently listed as the 30th. I am going to make it the Tuesday, the 18th at 11:59 p.m. And that's the same thing with this one. So y'all got more than enough time to do that one. And 24, it's currently listed as chapter 30, or excuse me, it's due on 7:30. I'm probably going to bring that a little closer too. Any other questions?
Nope, that's it. Have a good night.
You too. I'm going to stop sharing this and show you the due dates on the homework, so in case anybody wants to see them. And they'll also be on the video, so that's helpful. So yeah, these are the new dates. Notice I just changed chapter 22, and that's because not anybody requested it, just because it looked like you guys didn't remember that I had covered Gauss's law. So I figured I better give you a little bit more time. I didn't give you much because I did really cover it on Monday. So definitely make sure you get that done by the 14th. The 23 chapter 23 homework and conceptual are due Wednesday of next week, or excuse me, Tuesday, 11:59 p.m., which is the 18th of next week. So that should give you plenty of time to do chapter 23. 24 is currently listed as 7:30, but that will be probably changed to a little earlier date. The main thing is that if I don't leave an earlier date, then nobody's going to do it until literally the 30th, and we're going to have a test on chapter 24 before the 30th. So anybody have any questions? It's only Zhang left now. So you have any questions, Zhang? Yeah, okay. Well, have a good one, and I will see you on Wednesday. Feel free to let me know. By the way, you're the last one here, but I wish I would have told everybody. If you guys spend more than an hour on a particular problem, that's the time where you need to start considering, definitely asking your peers or other students in the class. But if you haven't heard from them yet, at the 1 hour mark, you need to go ahead and send me a text with photographs of the problem you're trying to work and some of your work, and I'll set you straight, because I don't want you spending more than an hour on a single homework problem in this level course. So now we've got this on videos.
Okay.
That'll help you help.
Yeah.
I'll let them know. Thank you so
Thank you.
much.
All right. Have a good one.
You too. Thank you.
Bye.